Hello everyone. Today I will be discussing an article which is published in Serious Science and Engineering Journal, authored by P. Mitra, Al Sundaresh and D. Subramanian. The title of the article is Stability of Inverter Based Resource Dominated Systems with Different Types of Local Load. There are two aims of this article. One is to highlight the issues which arise when grid following and grid forming inverters are incorporated in the power system in presence of local loads and their effect on voltage recovery after faults. And second, this article investigates the stability issues which may exist when synchronous generators are replaced by inverter based renewables. The flow of the presentation would be that I would be starting with the introduction, this test system description, simulation results, followed by the conclusion. So let's get started. So in the introduction, we'll be seeing the basic control structure of grid following and grid forming inverter. So in figure 1 shows the block diagram of grid following inverter, where we are getting the P reference from the plant controller, and after subtraction from the measured values, respective values, the difference is actually fed into the PQ block, which generates the ID command and IQ command. These ID and IQ command are then further subtracted from the actual ID and IQ current values, and they are fed into another block which generates the ET and EQ signals. These ET and EQ signals are in the DQ reference frame, which are converted into the ABC reference frame by using the theta. This theta is actually extracted by using a PLL, and the input of this PLL is actually a VABC, which we are taking from the grid and inverter VCC bus. In grid forming inverter, the case is a bit different. Here, after the error is actually the error between the reference and the actual power value is then fed to the PQ block. The PQ block actually has its own equations which generates the EDQ and the theta. This theta is then later on used to convert the DQ reference frame values into ABC reference frame, and this E theta actually generates the ID and IQ command, which is a bit different from what was happening in grid following inverter. So the major difference between a grid following and grid forming inverter is that in grid following, the reference, the theta and the voltage difference we are getting directly from the grid by using a PLL. However, in a grid forming inverter, we ourselves are providing the reference of voltage, and theta we are generating inside our loop. Now let's talk about how a grid following inverter and a grid forming inverter will work during normal and fault conditions. So we know that synchronous generators have a high short circuit capacity, that is, they are able to provide 4 to 7 or 3.5 to 4 current during transients. However, in case of IBRs, we generally have 1.2 to 1.5 per unit times of capacity only. So because of that, when there are faults in the system, we need to design current limiters. So because the moment the current passes, the moment the current is beyond the values of 1.2 to 1.5, the power electronic switch in our inverters will actually burn and it will damage the inverter. However, because of these current limiters, there is a bad effect on the voltage recovery after the fault. And if there are local loads present between the grid and our inverter, the case of voltage recovery will even get deteriorated, which we'll see in the following simulations, and which is the main crux of this whole article. So now if you see in figure A, the D axis is actually aligned with the terminal voltage VT, which we are getting from the grid and which are getting from the volt, even at the expense of active current, for good or proper voltage recovery or voltage support. So in that case, this is the figure B is actually the farmost or a specific case where all the inverter current is actually shifted to the reactive current, and this is the maximum current which the inverter can provide during fault. During this condition, we see that still the angle theta is maintained between the D axis and the real axis, and terminal voltage is aligned with the D-axis. Now let's talk about what will happen for a grid forming inverter. In grid forming inverter, we see that the D-axis is actually aligned, or the D-axis is actually where the internal voltage or the E inverter is aligned, and the terminal voltage is actually lagging behind the D-axis. And during the fault, in case of grid forming inverter, there will be a fixed amount of ID and IQ which the inverter can possibly maximum value which it can give. So in that case, we'll see that instead of maintaining the theta between the internal voltage E inverter, the angle theta would be maintained between the D component of the I inverter, which is ID inverter, and both the terminal voltage phasor and the internal voltage phasor will actually lag behind the D-axis. And this is actually happening because at that point of time the current has gone out of phase with the inverter, and this is the case which also happens with synchronous generators when there is a here we see that during fault in figure D, the angle theta is actually aligning itself with the D-axis, and instead of controlling the internal voltage E inverter, the inverter is actually controlling the current with ID inverter and IQ inverter as its D and Q components. And this is actually an abnormal condition where the active and reactive power output of the inverter can no longer be controlled unless we add some additional controls into the inverter. And it will be better to say that the current has become out of phase of the terminal voltage, and this condition is actually similar to when a synchronous machine rotor angle accelerate beyond 180 degrees, and this is the main issue with grid forming inverter under depressed voltage conditions, which will be further investigated. Now let's come to the test system description. So in this description, in this test case, the system has local loads, local generation, external generation, and there are different types, and two types of local loads are there, dynamic as well as static. One, like the total local load is about 158 megawatt, local generation is about 134 megawatt. We have three generators, G1, G2 and G3 of 14, 60 and 60 megawatt capacity. The external generation is about 625 megawatt with a local generation of 600 megawatt of its own. They are the local loads, which is the local loads are actually four types of local loads are considered. Initially they are dynamic and static loads. These which we are talking about are actually the dynamic loading, where the high inertia three-phase motors So let's talk about the test system. So here we have a local generation of 134 megawatt with generator 1, generator 2 and generator 3. They have 14 megawatt, 60 megawatt and 60 megawatt of capacity. External generation of 625 megawatt with a local generation of 600 megawatt. Now the basic focus of the study is the local loads. So there are total local load is about 158 megawatt, where 120 megawatt is for dynamic and 13 megawatt for static loading. The local loads are actually designed in four different ways. First is the high inertia three-phase motors, where the inertia constant varying from 0.6 to 1 second. Low inertia three-phase motors have the value of H from 0.1 to 0.4 seconds, and single-phase motors have inertia constant varying from 0.01 to 0.04 seconds. And the last type of local load, a local dynamic load, is actually variable speed drive. The SG model details are given, and GFL, GFM modeling are actually taken from the WEC guidelines. The relative and the related references are marked here. Now let us talk about the simulation result. So this whole study is very into two cases. First case is when the fault response is is when the post fault SCR value is 3.7, and the second is when the post fault SCR is 1.5. 3.7 means that the short SCR is actually the short circuit ratio, which is 3.7, which means it is a strong grid, and when the SCR is of 1.5 in case 2, that means it is a weak grid. In case 1, we have different types of studies. 4 types of studies have been done. Study 1 with high phase inertial loads. Study 2 is with three phase low inertial loads. Study 3 is single phase loads, and study 4 is with variable speed. And there is a special case where the maximum current limitation has been increased from 1.2 per unit to 1.9 per unit, and a 3-phase LG fault, which means a triple LG fault, is actually been done here for 5 cycles. And in case 2 where we have weak grid, we have the maximum current limitation from 1.9, and we, as I already told, that we have taken a reactive power priority system. And let's discuss the simulation results in detail. This is a simulation result for case 1 when high inertial loads are being attached. So at point 1 there is a fault for 5 cycles. There is a 3-phase to ground fault. That is triple LG fault is simulated at point 1 for 5 cycles. So 4 results can be seen. From the first result, which you can see, is that the system is stable for synchronous machine, grid following, inverter, and grid forming generation. Second result is, which we can see at the second dash block, that the synchronous machine has a noticeably oscillated response. This is because of the electromechanical modes which we have in synchronous machine that are actually absent in IBRs. Third point is that we see during fault, on fault voltage if we see that for synchronous machines the on fault voltage is higher, and for IBR it is much lower, and this is because of the high short circuit contribution of synchronous machine during fault than our IBRs. The fourth result was that we see that for GFL, in both the powers, active and reactive power, there are high transients into the system. This is because the priority change condition which we are using, of the operation which we are doing, is actually making the controller work aggressively during that small time, and because of which there are power oscillations. The second case with low inertial loads. So in low inertial loads we have 3 results. The first result, we see that the system is stable for synchronous generator and GFL, but not for GFM, which we can see that this red curve is actually oscillating. And this GFM failure is because the inverter is actually hitting its maximum current value, and which has led to loss of synchronism. The synchronous generator actually is stable here because there is high stator loading, and the GFL, the grid following inverter, is actually stable because of its group priority condition. Now if we compare the result, the voltage recovery condition, with the cases in the previous case, or in the previous study, which is study 1, we see that the voltage recovery is low, and this is because of high consumption of small motors. Because small motors, there is a rapid deceleration which is followed by acceleration during fault. Third study which we see is that at 3 seconds there is a certain increase in the voltage recovery. There is a certain increase in the active power injection of GFL, as well as there is a certain dip in the reactive power injection of the GFL. And this is because there is a quick re-acceleration of low inertia faults, which actually drops the Q-curve. So the effect which we are seeing is actually because of the inertia of the loads, which actually is the main attribute of this research, that whenever there is a low inertial load, there will be a slow voltage recovery, and the inertia and the loads will take some time. They will actually first, whenever there is disturbance, they will first this is a simulation result for case 1 when a high inertial loads are being attached. So at point 1 there is a fault for 5 seconds. There is a three phase to ground fault. It is triple LG fault. Is simulated at point 1 for 5 seconds. So 4 results can be seen. From the first result which you can see is that the system is stable for synchronous machine, grid following, inverter, and grid forming generation. Second result is which you can see at the second dash block, that the synchronous machine has a noticeably oscillated response. This is because of the electromechanical modes which we have in synchronous machine that are actually absent in IBRs. Third point is that we see during fault, on fault voltage if we see that for synchronous machines the on fault voltage is higher, and for IBR it is much lower, and this is because of the high short circuit contribution of synchronous machine during fault than our IBRs. The fourth result was that we see that for GFL in both the powers, active and reactive power, there are high transients into the system. This is because the priority change condition which we are using, of the operation which we are doing, is actually making the controller work aggressively during that small time, and because of which there are power oscillations. The second case with low inertial loads. So in low inertial loads we have 3 results. The first result, we see that the system is stable for synchronous generator and GFL, but not for GFM, which we can see that this red curve is actually oscillating. And this GFM failure is because the inverter is actually hitting its maximum current value, and which has led to loss of synchronism. The synchronous generator actually is stable here because there is high stator loading, and the GFL, the grid following inverter, is actually stable because of its group priority condition. Now if we compare the result, the voltage recovery condition, with the cases in the previous case or in the previous study, which is study 1, we see that the voltage recovery is low, and this is because of high consumption of small motors, because small motors, there is a rapid deceleration which is followed by acceleration during fault. Third study which we see is that at 3 seconds there is a certain increase in the voltage recovery, there is a certain increase in the active power injection of GFL, as well as there is a certain dip in the reactive power of the injection of the GFL. And this is because there is a quick re-acceleration of low inertia faults, which actually drops the Q-curve. So the effect which we are seeing is actually because of the inertia of the loads, which actually is the main attribute of this research, that whenever there is a low inertial load, there will be a slow voltage recovery, and the inertia and the loads will take some time. They will actually first, whenever there is disturbance, they will first
Now this is a special case where we have increased the maximum current limitation of our inverter based renewables from 1.2 per unit to 1.9 per unit. We have the same reactive power priority, and a similar triple LG fault is being done at 1 second, and the results are that we see that for this time the system is stable for synchronous machines, GFM as well as GFL. The voltage recovery is better than synchronous generators because the inverters can now inject more reactive power, which is no reactive power to support voltage. And if you see that at 0.9 in block 3, there is a dip in the voltage waveform, and this is because the GFL has a max upper limit of voltage, also, and when this upper limit of voltage is being hit, which is about 1.2, the system is then the voltage will dip, and then again it will start to rise. So after this first case, let's talk about the summary. So we say that if we let be irrespective of synchronous machines or inverters, whatever be the generation type, if we do not want to hinder the voltage recovery, in a strong grid, we have to see that this is only possible when we have large inertia motors or variable speed drives, because we see that low inertia motors or single phase motors which have lower inertia or lower inertia constants have a slower and poor voltage recovery. Also, since there is the GFL and GFM has low current capacity, if we are switching them to higher current capacity, we can get stable waveform or stable operation. Second, for when GFL inverters are used, system will be stable as long as we have a PLL which is working perfectly, and the voltage recovery will become poorer for single phase motors. We see that grid forming inverter is not able to work properly, or it becomes unstable because of hitting its maximum value. And for single phase motors, even the voltage recovery of GFL is even poorer as compared to synchronous machines.
Now let's come to case 2. In case 2, we see that the SCR has been reduced from 3.7 to 1.5, which actually is for weak grid. What is a weak grid? You can Google it out, or you can have some research papers. Weak grid is actually a system where even a small change in voltage can even lead to, or a small change in active power supply or reactive power supply can even lead to the instability of the whole system. So here, when we talk about high inertia, low inertia, and single phase loads, we see that if you have a proper size grid forming inverter and synchronous generators, they are suitable for connection in this these type of weak grids. We see that the GFL is actually the output of GFL, the voltage output, the power out, the voltage values is actually oscillating for GFL with all types of loading, and this is because the working of GFL is actually totally dependent on PLL, that is phase lock loop, and if the PLL is not working properly, our GFL will not give proper voltage or power. And here you see that GFM is actually working pretty well in V-grid system, and it is able to maintain the voltage. Now let's come to the conclusion of this whole article. So we see that when IBRs are in portions where their local loads are considered, and we don't want to have delayed or slow voltage recovery, even if the system is strong, both GFM and GFL technologies, they can perform well without any issues related to stability or loss of synchronism if we have a higher current capacity of GFMs. Second is that if we have a local load which predominantly is small motors or it has low inertia, then the voltage recovery will take time, and GFMs, if their current limit is hit, they will become unstable, and GFL will only work as long as PLL can track the system frequency properly. However, if we are increasing the current limits of GFM by oversizing the inverters, GFM can also help to operate stably, and it will improve the voltage recovery in that area. However, if we are increasing current limits of GFL, it will not enhance its stability in a weak system. However, it will help in having a better voltage recovery, which is necessary in some situations where where we have to prevent cascaded trip, but it will not enhance the stability of the device actually. And the last point would be that GFM inverters are more appropriate to install in weaker grids, and when you have a system which has local loads of variable inertia, it is better to have a grid forming inverter in a weak grid than using a grid following. That's all. Thank you. I know this article has a lot of loopholes which we can discuss later. However, if you have liked the video, please put a thumbs up. You can share it among your friends, colleagues, and Please subscribe to my channel for more such videos. If you have any doubts, you can put it in the comments. I will try to answer to them. Thank you and have a nice day.